Okay, now we observed, and we don't have a video of this, but I have other videos of it that I'll pull out for people to refer to with the same bottle, but probably in colder weather, because I think I did it last winter. Not a very cold day. Okay, we observed time, and the way we observed the time was interesting. And I'm not going to describe that right now. We'll do another video later where we kind of refine this. Okay, but we got time in steps. We had people walking around in circles, stepping, making tick marks for each step, and I just explained what I said I wasn't going to. And then every time the water got to a certain level, somebody yelled out mark, and instead of a tick mark, we'd use a check mark. And we counted those, and we collected that data down here, found medians, and found that these are our best group estimates of how long it took for the water to go, first of all, yeah. Something's wrong with this, but that's okay. We'll take it anyway. I don't have enough marks. So there's something wrong. Well, we'll have to fix this. But anyhow, let's assume this is right. That after 28 steps, we were at 150. Actually, we were at 150 at the very beginning. So something's wrong here, but we'll fix that. Okay, so we have these depths apparently at these times. At least that's what we're going to go with right now before we fix it. And we have these horizontal ranges. Okay? Horizontal range is how far the water went out before it hit the ground. And what we're just looking at right now is the horizontal range versus time. Okay? So, horizontal range is in inches, times in steps. Time then goes from 28 to 197. Actually, we'll just put an axis from 0 to 200 here. And I just mark this off using 32 as the highest number on the X scale. Actually, 25 is the biggest number. But it's really easy to divide 32 into half, and then divide that into half, and that into half, and so forth, and get a good result. So we get data points, okay? So let's just take what we've got here. This isn't quite right, but these are units of 50. So 28 would be about here, and we would be at 25, so we'd have a point like this. At 66, which would be around here, we'd have 19.5, which would put us, maybe about here. At 103, we've got 53, so 103 would be here. It's not 53, sorry, 13.5 gives us a point about here. 134 gives us 9.5. 134 would be about here, and 9.5 would be about here. 172, 1.5. 172 is going to be around here, and 1.5 is going to be around here. And then 197 gives us 0, so we have a point like here. Okay, now, I said that those points should lie pretty close to a straight line, and this is pretty close to a straight line, and we see that those points do lie pretty close to a straight line. So when we do a graph of what we actually think happened, now, let's be clear about this. We had a lot of variation in these counts, okay? And if everybody was pacing at the same rate, all the tick marks should have been simultaneous, right? So there's some uncertainty in the timing. When you average it out, I think we get pretty good results, okay? But there's still some uncertainty, and there's statistics involved with analyzing that uncertainty, and we don't go that deep into statistics. We just don't have time, okay? But we will talk about some about the statistics. So there are reasons to think that none of these points are really completely precise, okay? But starting with conservation of energy, our ideal model in physics tells us that this should be a straight line, okay? And it looks like it ought to be pretty close to a straight line. I mean, you know, I just plotted these by hand, right? And I didn't fudge it or anything. I just put the points where I thought they were, and it's pretty close to a straight line. So when we draw the graph, we don't draw point to point. That's ridiculous. We're just following our errors around. Okay? Although that's probably the way you were taught to graph.
Yeah.
When you have precise data, yes, you would do that, except what if you got a curve? Do you have polygon? You know, do you have straight lines? No. If you got a curve, by darn, you got a curve. Okay? So, you know, the way you're taught to graph isn't always the way we end up graphing, but there are reasons that when people first graph, you tell them to do that. Okay? There's nothing wrong with that. But I can draw a straight line here that I think best fits this stuff, and we'll talk more about what we mean by a best fit, but look at how close that line comes to all these points, and that was with a hand-drawn graph by somebody who doesn't draw that great. Okay? So here we have it. Here we have a linear model. Okay? Now we can also get a quadratic model for the depth, and we're going to write out those equations. We're going to be breaking for lunch in about 10 minutes, so we're not going to solve them, but these equations are really easy to solve. They're linear. You don't have to solve for one and get the other. You just add multiples of equations and equations, and pretty soon you solve them. And we'll do that. That one's easy.